Hello everyone, so let's see how our Gibbs energy changes when we are not at standard conditions. So the specific example that I have here looks at the decomposition of calcium carbonate into calcium oxide and carbon dioxide. And we're given the Gibbs energy of formation for the species involved in this decomposition reaction. Alright, so the first question asks, calculate the standard Gibbs energy of reaction and discuss whether the reaction is product favored at equilibrium. And then we're asked, is the reaction spontaneous when the partial pressure of carbon dioxide is 0.1 atmosphere in the presence of both calcium carbonate and calcium oxide? Alright, so those are the things that we have. So the first question is to calculate the standard Gibbs energy of reaction and discuss the product and reactant favoredness of the reaction. So because we're given the standard Gibbs energy of formation, we will use that to calculate the Gibbs energy of reaction. Right. So using the Gibbs energy of formation, we of course use the sum of them of the products minus the sum of the reactants, and we can calculate the standard Gibbs energy of reaction. So going ahead doing that, I obtained using the values given in the table, right? So none of them are pure species, so pure elements in their standard state, so none of them are zero. I obtained a value of 131.38 kilojoule per mole reaction. And right, and this is a positive value, right? So this is a positive value for the Gibbs energy, the standard Gibbs energy of reaction. So that means that we have a reactant favored equilibrium. Of course, at 298 Kelvin. All right, so yes, it's not product favored, it's reactant favored because our Gibbs energy is larger than zero. So calcium carbonate won't just spontaneously decompose at this temperature, and that forms a product favored equilibrium, and that kind of makes sense. That's why we have calcium carbonate under standard conditions. It remains a solid. Actually, why the Romans used it in their sort of form of what do they call it? Of concrete. No, okay, but anyway, that's neither here nor there. Just thought of that. Okay, but anyway. So the second part of the question is the reaction spontaneous when the partial pressure of the carbon dioxide is 0.1 atmosphere? All right, so now it asks us, so is there something that happens to the spontaneity of the reaction if we change something about the reaction conditions? So, and the way to determine spontaneity is, of course, we should stop looking at the standard Gibbs energy. We need to start looking at the sort of non-standard Gibbs energy, right? We need to look at the extent of the reaction. So what we need to look at here in the B question is we want to calculate the Gibbs energy of reaction, the non-standard Gibbs energy of reaction, and that we can calculate using the standard Gibbs energy plus RT ln of the reaction quotient, right? So we just calculated the standard Gibbs energy, right? We know what R is, we know what T is, and the only thing that we need the reaction quotient. So if we look at the reaction quotient for this reaction, it's of course products divided by reactants, we notice that only species that can have a concentration or a partial pressure is CO2. So that means the reaction quotient is just equal to the partial pressure of CO2, right? Multiplied by 1, representing the calcium oxide, and divided by 1 for the calcium carbonate. So both of those numbers are being absorbed in this expression. So Q is just the partial pressure of CO2. All right, so we can actually write it there. We can write it as follows. It's the standard Gibbs energy plus RT ln partial pressure, why did I write it as a row, of CO2. All right, and now we can just put in our values, because this we know is 381, of course, kilojoule per mole reaction, as we just calculated. And then we must take R. Now R is usually in joule per mole per Kelvin. So because we want to add it to a kilojoule quantity, let's take it to kilojoules. So make it 8.3145 times 10 to the negative 3 kilojoule per mole per Kelvin. All right. T is 298.15 Kelvin. And then our partial pressure, or our Q, is just the partial pressure of CO2, which we were given as 0.10, right? Atmosphere. Yeah, 0.10 atmosphere, because it's just the partial pressure of CO2. So taking all of that and then rounding it, so rounding it to the correct number of significant figures, I get 125.67 kilojoule per mole reaction. All right, which is slightly less. So in other words, it's, if you look at what the standard Gibbs energy is, it's 131, and this is now 125. So it means that a low pressure for the carbon dioxide does decrease the Gibbs energy. But the Gibbs energy is still positive, right? So delta Rg is still positive. So that means this reaction is not spontaneous. All right. Under these conditions, which are specifically that the partial pressure of CO2 is equal to 0.10 atmosphere, and that the temperature is equal to 298.15 Kelvin. Interestingly enough, if you look at what we're calculating, right, so that was the question. The question is the reaction spontaneous when the partial pressure is that? The answer is no, it's not spontaneous under these conditions. Why? Because the Gibbs energy is larger than 0. All right, so that's the question now. But thinking about this a little bit more, what can we change to perhaps make it spontaneous? Well, the first thing is we can perhaps change this temperature, right? Because if you put ln 0.10, you will notice that this is a negative value. So the first thing that we can change is we can keep this partial pressure the same, but we can perhaps increase the temperature. So see what value for temperature, just put in, for example, 1,000. Right? What happens if you make this 1,000? Do you get a negative value here? When do you get a negative value? What value of temperature? The other test is keep the temperature the same. What value of for the partial pressure makes this negative? It's going to be an interesting one, because you should get a very, very small value. It's like ln of 0.00000000001. And what does that imply? It means that there's basically no CO2 formed. So it means the reaction is only spontaneous when there's almost essentially no product. And the reason for that is because this is such a reactant favored equilibrium under these standard conditions. So when you keep the temperature at that, it means that the reaction will only be spontaneous to form the reactant favored equilibrium if there is no product. Right, so remember, a reaction can be spontaneous to form towards a reactant favored equilibrium only when there is no product from the beginning. So if you only start with the reactant. Right, and that's technically what a partial pressure of 0 means. So if you have a partial pressure of essentially 0, that means that the calcium carbonate, even though the equilibrium wants to predominantly form it, if you have no of the products, the equilibrium will, or the reaction will say, well, we have to form a little bit of it. So initially your spontaneity will be dictated and say, it will be spontaneous in this direction until the equilibrium sets in, which will be a reactant favored equilibrium, and it will predominantly still be the calcium carbonate which is present. And that is how the Gibbs energies work, is that you have a reactant favored equilibrium dictated by your standard Gibbs energy, that's what it tells you, and your non-standard Gibbs energy indicates to you what conditions are required to for spontaneity. So in other words, these conditions won't create a spontaneous reaction. It will be non-spontaneous because this pressure it means there's already too much of the product. So in other words, the reaction won't be spontaneous. In fact, the reverse reaction is spontaneous. All right. So that is what it infers to you. All right, so just think about what you can do and how what that actually means in terms of the actual system. I think that's a very good thought, or it shows real interpretation of these values and what the theory actually means. All right, good. Thank you for watching, and I'll see you in the next video.